afternoon, everyone. Thank you very much for joining us, either physically in campus or through Zoom. And I'm glad that there are so many participants. I think more are still coming in. According to our registration, we have more than 500 people registered for this seminar. And even the pandemic does not stop people from attending. And we are actually very glad today to have Professor Naaman to actually come and share his experience with us. He is a very senior academic and practicing engineer, and he has actually came to Singapore quite a number of times. So he's our close friend, and you know, he has been here so long that some of our professors who know him all have retired. And they're in the audience, like Prof. Tam and Prof. Gary Ong. Okay, and some of us are about to retire. So Professor Naaman actually graduated from Ehp Central Paris in 1964. Okay, then after that he went to MIT to do his MSc, MS and PhD. And he has published more than 350 publications in both journals and conference proceedings. And he has won many awards arising from his research. And he actually is, sorry, I didn't have the thing with me. I just go from memory. His technical professional contribution is also quite remarkable, being a fellow of an honorary member of ACI, and also fellow of other organizations like ASCE and Semen, yeah. Okay, and actually he's an expert in structural concrete and composites, especially in fiber reinforced cement. And he has just recently published a book on fiber reinforced cement and composites, concrete composites. Yeah, so without much further ado, we would like to invite Professor Naaman to give us a lecture on the path to ultimate high performance fiber reinforced concrete. He's here in NUS as the World Hub visiting professor, and this is actually the World Hub Distinguished Lecture Series, which we have quite a number of times for a few years already, and he's the first one for 2022. Professor Naaman, please.
Thank you. Thank you very much, Professor Quirk. I think I would like to add to my credential that effectively I have been a friend of NUS for many years. In fact, the first time I came here was around the late 80s. Professor Seng Lin Lee was at the time the chairman. Professor Tan visited me on a sabbatical in 1991 for 1 year. So we have been working at least for 30 years together. I also worked, I mean, when I say worked, I mean we worked on a project and published paper. I worked with Professor Paramasivam. I worked with late Professor Mansour. I had some work with Professor Ong, who is on ferrocement when he was organizing the Semen International Committee. I was at some point on sabbatical at the University of Singapore. I taught pre-stressed concrete. I taught a short course on partial pre-stressing with Professor Tan. I was examiner to the civil engineering department at some point. So my relation with the university has been a long term, and to tell you the truth, if Singapore was closer, it would be amazing for me if I could retire here and be close to my children, but it's too far. So first I start with Let me put the full screen here. All right, so first is greeting from the University of Michigan. You know that we are, all right, I'm losing my turn, okay. And this is the lecture. We are going to talk about the path to ultra-high performance fiber reinforced concrete. I say 5 decades of progress. In fact, I'm going more than 5 decades. You know, I'm older than that, so I can do it. But I would like first to express my gratitude to the National University of Singapore and the Civil Engineering Department, and in particular to the UHP consulting firm, because as Professor Quek mentioned, they provided the fellowship needed to pay for my expenses. It's a long way, and and I would like to say thanks again to Professor Tan for his resilience. We have decided about 2 years ago, actually June 2020, to offer the course on fiber reinforced concrete. And since then, it has been delayed 3-4 times. And every time we rescheduled, and with COVID, it couldn't be possible. And so I would like to thank you, Kang Hui, for holding up. And finally, we have a course, we are teaching it. And I would like to take the opportunity to thank the Becker Singapore Limited Company, because they offered the book to the students. And that was a significant cost that helped, therefore, in every case. So,
my apologies. It seems like my slides weren't advancing. So this is the first slides with greeting from the University of Michigan. This one is the title slide, The Path to Ultra-High Performance Fiber Reinforced Concrete. And this one is the acknowledgement to the National University of Singapore, to the UHP consulting firm, to my colleague and friend, Professor Kang Hui Tan, and for Becker Singapore Limited for their support. And now we go to the first slide of the presentation.
Assuming that maybe some of you are not familiar, and the definition is fiber reinforced concrete is a concrete with suitable discontinuous fibers added to it for the purpose of achieving a composite with a desired level of performance or in a particular property.
You want the laser, right?
Yes. I'm sorry, we just are still adjusting things. So I'm sorry for the interruption. Okay. So now, essentially, we have the matrix, we have the fiber, the bond between them, the composite. And of course, we want to put a fiber for the purpose of achieving a property of interest. Example, impact, example, shear resistance, and so on. Now, if you are in a civil engineering background and you are looking at courses, typically courses in concrete structures, we in general look at reinforcement, and today steel and FRP, fiber reinforced polymer reinforcement, are included. The cementitious matrix, the bond between them, the composite. And at this point, you have 2 paths. One is you go continuous reinforcement. That's reinforced concrete, pre-stressed concrete, partially pre-stressed concrete, textile reinforced concrete, etc. In fact, it started in 1855. First patent on reinforced concrete is on ferro cement, and it will come here in our discussion. And then you get all the application with all these wonderful structural materials. Some of them are standalone, some of them are in combination with others. We go back to this past where, from a mechanics viewpoint, you would expect that effectively discontinuous fibers are going to be different. They started by a patent in 1874. There was a dormant period. I'll explain it a little bit during the presentation. Then we started more scientifically working on the subject about in 1960. And then today we can say that also fiber reinforced concrete has some small standalone structural application. but certainly it could have a lot of application in combination with the other materials. If you are from a material science background and looking at fiber reinforced composites as a general family, you will divide them into brittle matrix composite and ductile matrix composite. The ductile matrix composite typically is your glass fiber reinforced resin, for instance, or carbon fiber reinforced epoxy. Brittle matrix composites would be ceramic matrices and cementitious matrices. And again, we go all the way to fiber reinforced concrete. So in both cases, we are looking at the material, but whether you go material science or civil engineering, sometimes it seems to fit differently. Same material. So we go back to the outline. I'll talk about some historical background, and I'm going to identify two periods in the life of fiber reinforced concrete. One, I call it a dormant period, and I'll try to explain it. The other I call a scientific period. And after scientific period started in the 1963, so when I say 5 decades of progress, it kind of starts at that point. I'll talk quickly about development of fibers and matrices, but I want to point out two key milestones. One is related to what we call today strain hardening FRC composite, and the other one is ultra high performance concrete or ultra high performance fiber reinforced concrete. So in fact, almost half the lecture will end up with ultra high performance concrete, ultra high performance fiber reinforced concrete. And then I'll talk about some of the application with UHPC and conclusion, hopefully in time. Now, starting with some history, you have heard, or I'm sure you have seen maybe, what we call Adobe Houses or Adobe structure made out of mud, clay, and straw. And I'm going to show you a picture of a typical village still today, where these houses are built of this adobe. And you would wonder why they have put the straw in the mud, in the clay mud. And very often you hear to strengthen it. But in fact, it should be interpreted not as a strengthening material. If you look at what these straws are doing, in fact, this is without the straw, you can see all kinds of cracks. But here too, you see the cracks. So what happened is that the straw is keeping the material from fragmenting or keeping the cracks from opening. Because remember, the material is subjected to temperature and environmental condition. It could be snow and rain and heat. And what seemed to be a great advantage of the straw here is that indeed they keep the material from fragmenting, and as a result, it's a better material for the purpose of this construction. I go back to the fibers in construction material history. We know that asbestos fibers were used in ceramics found in Scandinavia. And the assumption, of course, we don't know what the ancient people at the time thought, but the assumption was that the fibers stabilized the ceramic when they heated it to, to form it in its final form. We also know that horsehair was used in mud to produce some, for instance, bricks-like material, cow manure with straw have been used. Okay, so this is the background in terms of material other than concrete and steel. First patent of steel fiber in concrete was taken in the 19th century by a man named Berard from California, surprisingly. And really what Berard had in mind was to use steel shavings, which were from the waste from steel mills in concrete, and he used concrete blocks. And of course, the idea was to strengthen the concrete blocks. And this issue of strength is important. So let me look at history now. starting by this patent of Berar, 1874. This is my time axis. It's going to span until today. And I go first in a period I call Dormant Period. This is not dormant in a sense, nothing happened. It's a dormant, and I'll show you, in a sense that there were development, but they were not convincing and the industry didn't pick up. Then I refer to what I call a first scientific study by a group of researchers. The professor was Professor Romualdi, Carnegie Mellon University, 1963. I'll explain why this study is important, although the assumption was wrong, but it's important. And then I'll identify a second period, starting at this point. Notice in the 1960s, we started having testing machine, we started having load cell, we could test load deflection curve, we started having extensometer and LVDTs, and later on optical system to track deformation. So that's why I call this the beginning, the modern development where scientific approach is used. Now, along here, I'm going to address one milestone actually, strain hardening, strain softening material. You will see it, although you may know what it is, but you will see the background of it. And then I will talk about UHPC, UHP-FRC. It seemed to start around 2003. It started a little bit earlier, and I'll explain that. All right, so now let's look at that period that I call Dormant Period. And it went from the first patent, 1874 to 1973. I want to show you here some patents that were developed submitted by many people. This one, for instance, a ferrocrete construction. They use flat steel fibers, basically cut in short pieces to strengthen corbels. And it is today, if you give me a fiber like that, I say, yes, it does, it will do a good function. In this patent, 1912, the main assumption, or at least the main suggestion, was that you needed to create better bond between the reinforcement and the matrix, and these annuli, if you want, created that bond. The same some ideas we have today about how to improve the anchorage of fibers. I like these two patents very much. 1927, this is a method of producing a pipe. In fact, pipes and poles is a good application for fiber reinforced concrete. And Mr. Martin suggested fiber of different lengths, and then crimped fiber. We know crimped fiber today gives you certainly better bond because of the mechanical anchorage. But this patent could be done today. And again, it's called method of forming a pipe. In 1933, we have a patent by Etheridge. And I like very much what Etheridge wrote. He wrote, he want to use the fibers to stitch the cracks in concrete. So there is a crack is going to form, and he want to stitch the crack, which is, again, what we try to do today. But I will explain why they were not successful. And now I have two more patents. I just show them here. One by Mr. Constantinescu. In fact, he almost took every single, I'm showing only one figure. He almost took every single patent that happened before him and claimed it, with the difference that instead of having a straight fiber, he coiled it. So this is a new idea. You coil, you have a third dimension if you want. And I think what he did could be also valid today. And then you wonder why we haven't heard of him. And at some point, I was working as a student at MIT, and we needed to create an anchorage for fibers. It's a long story. And I developed this almost like a football fiber. where if you have a crack, obviously, most of it, there will be sufficient aggregate. Imagine you go in the middle and this will anchor on both sides of the crack. Has never been used, but it's in there, I mentioned. Now let's go to more modern fibers. I show you this, although I want to go back and talk about the dormant period, but so we can finish from this presentation on the fibers. Today's modern fibers could be simply cut from wire. They could be deformed, indented. They could have paddles at the end, buttons, hooks, twisted, and so on, or double hook. Today, again, fibers can be steel. I have 4 of them on the periphery, or maybe carbon, Kevlar, Spectra. Spectra is a high-density polyethylene. The trade name is Spectra in the US, but it is somewhere else. It could be Dyneema or something. And I have also another set of fibers that we could use. It's going to be very modern fibers to use. I like to call anything below 50 micrometer a microfiber. So I have carbon microfibers, I have PVA microfibers, I have even some steel microfibers in the shape of steel wool, etc. So all these are available today if you want to use fibers. And this fiber that I show particularly because we are going to talk about ultra high performance concrete. This is the type of fiber currently used mostly in ultra high performance concrete. They have a small diameter, 0.12 to 0.3 millimeter. You know, in producing steel fibers, when you go to small diameter, it is very expensive because you have to draw the fiber through different dyes. It's not like a glass fiber, you let it flow and it becomes smaller and smaller diameter. So for ultra high performance concrete, we have fibers with relatively small diameter, aspect ratio that is length over diameter in the range 40 to 100, tensile strength up to 3,000 megapascal. So I just mentioned this to make sure that when we talk about fiber, ultra high performance concrete, it's not just a round of the mill fiber that you would use. All right, and now I go back to that first period, which was when fibers were introduced and nothing happened for a long time. If you try to look at how long it took, there is something missing. What is the market penetration of different materials that we know today in the market? I mean, it took reinforced concrete. 1855 was the first patent officially, although ferrocement started 1849 by Lambeau building his boat, but the patent was 1855. And yet, within 20 years, we have an aqueduct, Lavin in France. We have several structures along the Suez Canal. We have the lighthouse foundation of the city of Port Said. All these were built in reinforced concrete. So 20 years later, you had quite large structure being built. You take pre-stressed concrete, the Freycinet's patent, 1927. 20 years later, you have bridges built all over in France and in Europe. In fact, the first one in the United States, 1949. So that's about 22 years later. And now we take fiber reinforced concrete, 1874, and almost 9 decades until 1960, although we have all these nice patents on the fibers, and we had good concrete because the concrete was used for reinforced concrete and pre-stressed concrete and so on. And yet, nothing happened with fiber reinforced concrete. And then you have to ask yourself why. And I say that the following, that the initial idea of steel fiber in concrete claimed primarily some kind of strengthening. In fact, I think in the 1800, 1900, or even the beginning of maybe the 2000, the 1900, people would, even if something was toughening, people would say strengthening. Yeah, I'm going to put the fiber in concrete. Why? It's better. What does it do? It strengthens it. Okay. But so they use the term, and many have used the term strengthening of concrete. And strengthening could not be proven in field tests And I'll show you the type of field test they did. I didn't have an old photograph. Sometimes what you see is you see a beam, and then you see a number of people standing on top to prove that the beam is good. I know there are some photos like this. I couldn't find one for this presentation, but I'm showing an example of a beam being tested by the same method they would have tested in the 1870s and 1900s. That is, putting the beam and putting a bunch of bags on top, sandbags, until it failed. And we call this method of loading a load controlled beam, because once you have to put the load, that's it, the load stays there. And what you get, you may get an answer like this up to this point, maximum load, and the load then, the beam supposedly deflect or fails, and you don't get anything else from a load control test. Or what you end up is your sandbags are there. So now let's really look at the real method of testing a beam is what we would call today a deflection control test. And in the deflection control test, you get not only the maximum point, but you get the resistance of the beam up to whatever deflection you go. So now let's assume that I have three beams. One is C1 giving me this kind of curve, C2 this one, and C3 this one. All of them have the same maximum load. So if I put sandbags on every one of these beams, they will seem to me that they fail at the same load. So true, they fail at the same load. However, if I run a deflection control, I would see that obviously this C3 is almost elastic plastic and is really a very good material. And C2 is better than C1. So I would be able to make a rational judgment as to why one is better than the other. Yet from a load viewpoint, all of them are the same. Now, when we look at the area under the load deflection curve, we associate that with toughness, energy absorption capacity. And so what we could really say that the tests that were run earlier during the life of fiber reinforced concrete did not identify the contribution of the fiber to toughness and ductility, or they were not able to measure it. And as a result, in fact, it was a failure. So observation, what happened 74 and 60, we could say that suitable fibers were developed and we had okay matrices. Fiber reinforced concrete beam did not meet expectation in terms of strength because they didn't know how to measure energy and toughness. So they said they are not good. The profession did not understand the importance of energy absorption. While the profession, once they tested with sandbag, they said, okay, it's not good, I'm not interested. So what we could also almost say, many of the patent or the patenteur, those who have submitted patent, had good ideas, but there was no theory, there was no scientific fundamentals behind these ideas. And that might explain why they failed. So now I go back to my time axis here, and I mentioned that 1963, we had what I call the first scientific method or the first scientific study on fiber reinforced concrete. By the way, if any one of you knows of an earlier study specifically on fiber reinforced concrete, scientific study, not somebody just mixing fiber, please let me know, because I would like to know. But this, for me, this is it. So the second period starts here, and I will describe the first paper that triggered this movement. In 1963, from Batson and Mandel, at the time, Batson and Mandel were students, then Professor Batson went on his own. They published a paper in which they said that if you put fibers in concrete, the strength of the concrete increases as an inverse proportion of the square root of the spacing of the fiber. Now, let me immediately say, the spacing of the fiber is not difficult to calculate. You could easily calculate the spacing if all the fibers are parallel, if they are random in plane or random in space. It is done. So we know how to do that. We know how to calculate the spacing, and they did it. They gave us those numbers. But so we have, for example, this is the spacing, and their theory said sigma, the strength of the material, is some kind of constant divided by the square root of the spacing. So if you today are an engineer looking at this, you would be very excited. You say, my God, you know, all what I have to do is reduce the spacing, and I get very high strength. Now, first, let's see why they came up with this idea. Now, remember, in the 1920s, Griffiths, a British researcher, introduced the concept of fracture mechanics. And between 1920s and 60s, that was a very, very serious concept. You know, it was followed at many universities. Maybe you don't remember, but there was at some point the Comet, which is a jet plane introduced by the British in the 1950s. Two of the plane blew up in midair, and it turned out it was a fracture problem of the glass. So the fracture mechanics was very much followed. And of course, in the case of, the fracture mechanics condition that Griffiths had developed, stress the strength of the material, if you want, is some kind of constant. This constant is called fracture toughness mode 1 cracking, whatever. But anyway, some kind of constant divided by the square root of pi A. Pi 3.14 A is half the crack size of, you know, assuming you have a flaw crack, half of course, the initial assumption was a penny-shaped crack. But anyway, half the crack length, say, in a concrete concept is used. And effectively, Griffiths showed that this relation holds. When the cracks decreased, the strength increased significantly. So it was very, very fine glass fibers. The strength of that fiber was much larger, much higher, according to the relation, than if the fiber diameter was bigger. So you could say Romualdi and Batson used the same idea. They picked up a constant, and instead of using the crack size, they used the spacing of the fiber. In their mind, the crack goes between one fiber and the other and is arrested there. It's not going to go anywhere. But in fact, we know it's not true. It's not get arrested by one fiber. It keeps going. And so the initial assumptions, if somebody applied their theory, was that it will go this way. The strength will go very high. But in fact, it didn't. And I show you that in the next slide. So in the 1960s, if you took this new publication by Dr. Romualdi, applied it to plain concrete, let's say, with a strength of 2.1 megapascal, and then added, I can't remember the exact volume, fibers in such a way that the spacing of the fiber is 6 millimeters, it told you your strength in tension increases to 18.7 megapascal. Now, let me tell you, this was very exciting for a lot of researchers, because if we can get concrete at 18.7 megapascal in tension, we can use it without reinforcement. You know, it's a structural material. So, however, the first scientific studies now, as soon as Romualdi published the paper, and there was a lot of excitement. In fact, he got a patent. He got several research projects from the Department of Defense and other departments. And then there was a small publication, not a small, a publication, I mean, first publication by Professor Shah and his student, and they tried to verify the theory, and their data showed that yeah, you could decrease the spacing, but the strength doesn't increase very much. It increases a little bit, but nothing according to this. In fact, well, my own work, which at MIT started in '69, and my thesis was on a statistical theory of strength of fiber reinforced concrete. I can tell you at the time it was too futuristic. When my advisor told me, "You're going to work on fiber reinforced concrete," I said, "Why? I'm interested in pre-stressed concrete. You know, why would I go cut the wire, cut the fiber?" But anyway, it was, you know, my advisor said, you know, he's paying for my studies, so I did. So this, and I ran quite a large number of tensile tests, direct tensile tests. And at the time, even using an Instron universal testing machine, we would use the machine to get load and displacement, but the displacement was between the platens, was not like an LVDT taking exact strain. And you could then understand what the shape of these curves are. But typically what I observe, and 3% fiber is about as much as I could put from the fibers I had. What I observed something like this: this load increases up to a certain point. There is a crack that happens. So I call this the cracking strength. And then it decreases up to this point, and then it decreases, go back in a softening way. Along this part, the fibers pull out. I call this the maximum post-cracking strength. This is the cracking strength. I observe here, if you look PSI, about 2 megapascal, maybe 3 megapascal. But the theory of Romualdi would have given me 35 megapascal, according to my numbers. So obviously this was not correct. But because the idea of fracture toughness was introduced, because of the interest of the scientific community in getting a material that can get more fracture energy, it generated a lot of interest. And so I explained maybe when I was a student at MIT that my professor could pay for me to do the research. It came from somewhere. And particularly, as I mentioned, the Department of Defense was interested in defensive structures, impact resistant structure. At that time, we started working on seismic resistant structure. Anybody who needed a structure that can absorb energy was immediately interested in fiber reinforced concrete. And in fact, as you know, even if today you give me an assignment to work on the tension of fiber reinforced concrete, or to work on the fracture, let's say, I might during that study, I will learn more about tension, compression, shear, whatever, because that's part of the study. So eventually in '83, I'm showing this because it's a visual. Eventually in '83, we ran some fracture toughness tests using double cantilever beam, large ones. And I show you this result, which shows here what we call the apparent critical fracture energy. For the mortar, 0.5, whatever the number, don't worry about the number. For 1% of this particular steel fiber, 45. So in a way, by putting 1% steel fibers, I'm observing 90 times the energy, not 90%, 90 times the energy absorption capacity, or if you want, 90 times the surface energy of the material. Okay. Today, we can do 1,000 times. Okay, and we did it with Sifcon and some other material. But so it's not anymore that the energy is a little thing. The energy became, or fracture energy, or the toughness of the material, became the real key parameter, the key most important parameter. And it has to be so. So I stop here in a history pause. While we were evaluating the fracture energy of FRC composite using scientific method, we also worked simultaneously on the mechanics of the composite, fracture mechanics, strength, post-cracking strength, etc. So the pioneering idea to increase tensile strength now understood after initial cracking. The idea in the first pioneer simply looked at the cracking strength, and that didn't change very much when you put 0.5% fiber or 2% or 1% fiber. But after initial cracking, that was the key. They didn't understand it, but now we understand it. And so after this initial cracking, we get something, I call this the maximum post-cracking stress in a tensile test, or the modulus of rupture in a bending test. That became understood and the best part. Now, today, when I want to characterize fiber reinforced concrete in general from a performance viewpoint, I can say it is strain softening or strain hardening. Now, strain softening is a little bit like this curve here. This is deflection softening, but in a way, after cracking, the load drops and it never picks up more than the cracking load. So I show here today definition of strain softening response, which is you reach the point at which you have a crack, the load drops, maybe it increases this way or this way, but in any case, always the maximum post-cracking stress is less than the cracking stress. So this is a definition that in fact started only 20 years ago, 15 years ago. Before that, we didn't have it, but I show you why we had this issue. Between 1963 and 1968, if you reviewed all the possible publications that were published on the tensile response of fiber reinforced concrete, you will find what we call today strain softening behavior. In 1978, in collaboration with Professor Shaw, we published a paper at an international symposium in the UK, organized by Riley. And effectively, this was the first time we had tested tensile specimen in tension, fiber reinforced in tension. And we observed several cracks. We observed this load maximum after cracking larger than the load at cracking. We even were so interested that we measured somehow the width of each crack and the order in which they came. At the time, we looked at this. I said, this is great. We called it desirable multiple cracking behavior. We didn't call it strain hardening, as later on we will. But we tried something. In fact, later on, today, using all our knowledge, we call this behavior a strain hardening behavior. It means after initial cracking here, I call it percolation cracking, meaning you have a crack going all the way through the specimen. I have a hardening region, that is the stress increases above the cracking stress. Multiple crack occur up to a maximum point, calling the peak load. At this point, there is what we call localization. That is one of the cracks here becomes weaker. Imagine you have a chain and one link starts opening. That's localization. And then the specimen, the response softened over what we call a softening branch. And that softening branch is accompanied by either fibers pulling out or fiber failures or a combination of both. So today, this is understood as strain hardening behavior. But at the time, we really didn't know. We called it desirable multiple cracking. In fact, again, today, this is an example of a strain hardening response. You could see clearly first cracking, maximum post-cracking stress. The specimen has been spread here with alcohol so we can take a good picture of where the cracks are. And, 10 megapascal in direct tension and sufficient ductility is a very, very good response. But this is a real specimen. Now let's go back to our, time axis. Between 1963 and 2003, In 1987, I was working on SIFCON for several years. And I was observing strain hardening behavior. I mean, it was beautiful, 1% to 2% strain at maximum stress. And I presented a paper, and I decided to call this high performance. Now remember, this is 1987. Later on, with Professor Reinhardt, we organized 6, eventually every 3 years, international workshops on high performance fiber reinforced cement composite. In our mind, what we call today strain hardening, but at the time we didn't have that clear definition. Just to make the story short, at the high performance fiber reinforced cement composite number 4, at the end of the workshop, we all assembled together and we decided that all fiber reinforced cement composites must be classified according to their tensile response, either strain softening or strain hardening. No need to go in detail. This is a performance specification. You could do it by using PVA fiber or steel fiber or whatever. You don't need to create a name, SIFCON or whatever, ECC or whatever for any of your developer. Just call it strain hardening, give the information, or strain softening. So you notice it took 40 years. This is a scientific community, 1963 to 2003, to come up with this definition. And in fact, as a result, we had deflection softening and deflection hardening. So it follows from tension softening to deflection and so on. And the sketch for it is shown here. All FRC composite are strain hardening or strain softening. Some of the strain softening can give you deflection hardening. All the strain softening give you deflection hardening, and so on. You get deflection softening. This is a visual of tension and compression. And you would agree with me that let's look at deflection, because this is a common application, a small beam, a small slab. You would agree with me that if you have a response like this of a given construction material, you could use it for some structural application, because you could use your service condition here. You have maybe a factor of 2 for the ultimate. Ultimate is not brittle. You have a descending branch that gives you warning. So it is a structural material that I can use, but it has to be deflection hardening, not softening or strain hardening or softening. Okay. So what I could say today is that strain hardening implied possible standalone structural applications, that beam, bridges, slab, tanks, similarly to a conventional reinforced concrete or pre-stressed concrete. Of course, maybe not the same load capacity, but in a similar way on a different scale. And this little example shows that if I look at it and I didn't have a scale, I say this is a perfectly good structural material that I can use. Okay, so now I'm switching to the case of UHPC, UHP-FRC. Looking at the chart again, this is my time chart. We started with strain softening, we ended up with strain hardening. And UHPC started, I'll show you a little bit earlier, but the serious UHPC really started about early 2000. All right, by nature, we are all competitive. The Olympics every few years, but even in technology, we like to always get higher strength, higher ductility, higher toughness, etc., etc. And today, in the field of fiber reinforced concrete, it's UHPC. UHPC, ultra high performance concrete, or UHP-FRC, ultra high performance fiber reinforced concrete. In fact, there is the same. You cannot use UHPC without the fibers. And I'll explain a little bit that when we talk about the definition. So the outline of this part, I'll define UHPC and its history. I'll give an example, not in terms of many details, just an example of suffering, how it took us at the University of Michigan to develop our own mixture, successful mixture. Conclusion, and the example of application I'll give you just few to give you an idea what's going on at this time. The first definition we have, although we had UHPC existed before 2008, but the first definition attempted was given by Dr. Rossi from France in one of his papers. And he wrote the following: UHPC uses a relatively high binder ratio, a water to binder ratio less than about 0.2, and shows a compressive strength in excess of 150 megapascal. Let me explain each one of them. High binder ratio, the binder is essentially your cement, but if you are using silica fume or if you are using other cementitious additive, well, that's the binder. When you say high binder ratio, you basically could translate that high cement content, okay, compared to the aggregate, okay, so it's all by ratio. Water binder ratio less than 0.2. If you took a course on concrete technology like I took 50 years ago, you are told, say you take 1 cement, 2 sand, 3 aggregate, 0.5 water cement ratio. Because whether 0.5 was kind of flip a coin and you get it. You also were told that even chemically, the cement needed the water cement ratio 0.27. So in other words, for all the chemical reaction to occur, you needed to put 0.27. So we never really thought of putting less than 0.27. And then the last item, the compressive strength more than 150 megapascal. So we had at least one definition, and I like it because at least somebody stood and said, this is what it is. Now, 10 years later, and this is ACI Committee 239, 10 years later, ACI Committee 239 came up with a definition. And let me read it. Ultra high performance concrete is a concrete that has a minimum specified compressive strength of 150 megapascal with specified durability, specified tensile ductility, and specified toughness requirements. These are all specified. It's like a performance requirement. Fibers are generally included to achieve these specified requirements. So, in a way, they made it one single requirement, 150 megapascal, but all the rest is a performance requirement specified by you. And the specification could be, if I was specifying, I would specify at least a strain hardening material. I want that. It could be deflection hardening. I may specify some durability or fracture toughness, whatever. The difficulty here is that when this ACI committee, and I was on the committee trying to define UHPC, and I was of the opinion, let's define UHPC and then UHP-FRC. And they thought that you cannot use UHPC without putting the fiber. People are going to get confused. Let's put them together. And it's okay. So, but sometime in my own, when I want to make sure, if I'm putting fiber, I say UHP-FRC. That's what I mean. But anyway, what's important here is ACI kept it up to the user to specify the requirement. Okay? Unlike the case of Rossi. Now, I would like to immediately say that by 2000, the ACI was 2018. By 2022, we have had some relaxation, I would say, of some of these requirements. The first, ASTM, in one of its recent standards, I can't remember the number, specified that UHPC should be more than 125 megapascal. Okay, so that's a little bit of relaxation here with respect to 150. Dr. Graybill, if you are doing research on UHPC, probably you have seen some of his paper current at FHWA in the US. And in his own test, although he followed 150 megapascal, but you run a test or whatever, you get less. What do you call that? So he said, I'm going to call that UHPC class material. So basically, we have used the same component, the same material, but we were not lucky to get 150, we got 130. Now, more boldly, recently, Professor Tadros, a good friend of mine, and he was commissioned by a project from the Precast Prestressed Concrete Institute for a large project, actually. His report was published in December. At some point, if you are interested, you might be able to get it from PCI or from him. So from the beginning, he decided that they are going to, he's working now for a precast pre-stress application. And from the beginning, talking to many people in the precast industry, etc., they targeted 120 megapascal for two reasons. One, we don't need more. Two, it costs less. And cost was very, very important. So now what we have is from Professor Tadros' study, we have a UHPC that he gives you the proportion, guaranteed to give you 120 megapascal. He gives you the design recommendation. What do you use in the case of a beam design? What's the modulus of rupture you can expect? What the ductility you can expect, etc. So he went all the way through, designed several structures, and it was for the US, I mean, it was a relatively large money project for a research study without. So anyway, I just mentioned here that in Japan, they still use the term UHSC, ultra high performance, ultra high strength concrete, and it's 180 megapascal. But for us, I think what I'm mentioning here is that if you have a test and you have targeted 150, but you get 145, don't panic, call it UHPC class, and you are in good shape. Okay, this is an example of an actual UHPC stress strain curve obtained from a recent study by Abra Shamba and a colleague. And the reason this is here is I was interested at some point in studies the strain capacity of this material, but you could see it's just beautiful. In this case, the fiber have been oriented, that you get a beautiful stress and strain response, strain hardening, reasonable strain capacity at the maximum, and so on. So it's just 2% steel fibers, the strength 140 to 150 megapascal. So it satisfies the requirement. It is the UHPC. Now I apologize for this slide. It's busy, but I will take the time to explain. And the slide represents time scale, horizontal, going this way, then of course coming and going back. So we are going to span here about 50 years. And mention first that since 50 years, people have been trying to get high strength concrete. And one of the first study here, Udenfoyn and Roy, in 1972, published a study that they have achieved 500 megapascal. And this is very exciting, of course, except when you went and looked at the details, they used 8 millimeter or something specimen. They heat cured it, pressure, devacuum, etc. So it was a good record if you want, but it was not very practical because you very well know that if you have a very small specimen, when you go to scale, things change completely. In 1981, a study by Burchell et al. That came out from the UK on what they called micro defect free cement. Okay, that was my time already. I'm interested in what everything is going on. And we were excited until we found out that, and they said we have 200 megapascal. But then we found out that they used polymer in addition to the cement, and they had some other curing and heating procedures. And so it was a very specified special product, but it was not the cement, completely cement. If you put half of it is polymer, it's not exactly cement. In the 1980s, several researchers, I give names, Bakke in Denmark, Young in the US, Aitken in Canada, Jennings in all were working on what they call densified small particle cement. And for us today, basically cement with added to it something like silica fume to densify the combination, or granulated blast furnace, like ground, etc. Cementitious additives on a smaller in a smaller particles, and they claim 150 megapascal. So that's good. Now, between 1981 and 83, I mentioned in particular, Barker is a researcher, worked at the cement company in Denmark, and has done tremendously good research in that field. So he was working here, and in 81, 83, Barker obtained a patent for a material called Densit, basically a fiber reinforced concrete. In fact, basically an ultra high performance fiber reinforced concrete. He claimed 120 to 250 megapascal. And eventually, of course, Densit was used not only on its own, but here I mentioned Barker. He used it in very heavily reinforced concrete beams, like reinforced in both compression and tension, and using Densit in it. And that material was called compact reinforced concrete. But it was reinforced concrete, but the matrix was Densit. Now, at the same time, actually not doing between 80 and 90, I was working on a fiber reinforced concrete Sifcon. Sifcon is basically you put the fibers in a mold, you infiltrate with a slurry paste or whatever, cement paste, and you get you wait till it hardens, you get your Sifcon. That Sifcon has the highest possible fiber content you could put because you fill it up. There is nothing you could do. And we were getting at the time 70 to 140 megapascal. At the time, I was not as much interested in the matrix. We used simply cement, fly ash, fine sand, and water reducing admixture. At the time, there was not enough superplasticized. But I mention it here because it's at the same time, somehow, Barker was doing a better job on the matrix. I was mostly interested in Sifcon. Now let's move to 1994. And here I have three studies, 94, 95, 98. Both of the three of them generated from France, from three laboratories that are within a short distance of each other. And the reason is that they knew each other. Delarare worked at the Laboratoire Central des Ponts et Chaussées, which is like the test lab of the university, bridges and highways. Richard and Cherezy were working in a big company called Bouygues, and Chanviard and Belloul were working at Lafarge. And within 4 years, the first person who used the term ultra high performance concrete was Delarare with his colleague, Professor Souter. And Delarare, in his study, mentioned what Barker has done earlier. He said that you need to work on high packing density of the matrix in order to achieve this high strength, 236 megapascal. Now, again, simultaneously, almost at the same time, Bouygues published a paper saying we got 800 megapascal. However, that 800 megapascal was obtained with added polymers on small specimen, etc. In fact, their equivalent 200 megapascal was a little bit, they had several materials, but one of them was 200, required some heat curing, of course, some specific formulation because it's all secret at this point, but also particle packing was mentioned as being very important, how to do particle packing. And then Lafarge study, but Lafarge was, 1998, Lafarge was bold in terms of putting on the market the product called ductile. Ductile in France, ductile in the US. Basically, they put in a bag your ultra high performance concrete mixture. They said, if you buy our bag, you use it under, at the time, in the beginning, it was under our supervision because they wanted to make sure you don't add more water, etc. We will guarantee 200 megapascal. And it wasn't long before people who, I mean, even industrialists or construction company who needed some very special application, who bought the material effectively could verify that that material gave 200 megapascal. So to me, I credit Lafarge being the first to put that material on the market, and then it created a hoopla, because now every one of us who is doing research on fiber reinforced concrete since 20 or 30 years is saying, why cannot I cannot do that? You know, I understand what's going on. And I think the main, in my opinion, the main thing that was missing was this packing density issue and maybe a few other things, but we could have done. So now, as soon as Lafarge published this, I show here 2021, it would be 2022. A lot of people got into the race, if you want. We got materials called Semtech, Serasem, Cardiff FRC, and I give names. Dr. Rossi, Professor Karihalo. Most importantly, several people started obtaining these mixtures and publishing. This is what I got. So now it's not proprietary anymore. Remember, ductile was proprietary. You didn't know what's inside, you bought it. Here, a lot of non-proprietary, and I give some name, Professor Schmidt from Germany, Dr. Ho, who is in Malaysia. I'll mention him later. Dr. Kim, Korea, Failing in Germany, my student, Willie, in the United States, Naaman, myself, my colleague, Tadros, I just mentioned, and Gravy. All of these guys worked on new mixture and published them. So, you know, if you follow these mixture, you do it. But again, I go back here at this part, the importance of particle density or packing density and how fine particle packings are used. So now I'm going to show you a little bit what I'm going to talk about particle packing, but the rest is kind of, we talked about already. Let me skip this. Oh. Now, starting in the year 2000, and armed with the new studies that I was reading from Lafarge, et cetera, just give me time. I decided to start working with my student on ultra high performance concrete, and we ran a very systematic evaluation. Meaning we studied seven different types of cement, 5 sources of superplasticizer, 5 sources of silica fume, and so on, thousands of tests. And it took us about 3, 4, 5 years before we started getting some interesting results. So the study took about 10 years total. So at the end, we had some very nice results. But I want to mention something that we don't think about, and that's the packing density optimization. And if you haven't done it before, this is visual and you might like it. This is, if you want, when you put spheres of equal diameter in a container, their packing density turns out to be about 60%. That is, the volume of the sphere inside the volume of the container is 60%. However, if you organize these or you put them in this pyramidal form, it's called ordered hexagonal close pack structure, like this, then you get 74%. And this particular result was already obtained by a mathematician called Kepler, named Kepler, in 1611. In fact, he gave the formula. The packing density of an ordered structure, the way I showed it, is pi over square root of 18, and that's 74%. Not only that, he then calculated the diameter of these little spheres that you could fit in the interstitial space between the bigger sphere, calculated the diameter, calculated their volume, and he said if you put them all in these spaces, you get 1.7% more. So you go from 74% to 75.7%. That's not much. was putting all this. But that tells you that if you want to increase the packing density, you better think hardly about it. So now I go to this study, which was carried out by Yamada, I guess, can't remember, maybe 2005 or something like that. And in his study, he imagined that these big spheres here are red blood cells, and he wanted to add to them small particles of medication. And he ran a very large number of simulations, and he was able to then get the radius or the diameter of the particle that he needed to add to these spheres to get the highest possible packing density. Okay, so I took this, calculated, for an example, taking a column of 300 millimeter, I took the diameter of the big sphere here, 0.5 millimeter, and I got D3 1.1 micron. Very small, but by using this, I might be able to increase the packing density to 80%. Okay. So now this is typically what we selected for our mixture. This is the size. This is here 1 millimeter or 1,000 micron. In our study, the mixed study at the University of Michigan, we selected D1 0.5 millimeter, D2 calculated by Kepler's formula, D3 calculated by Yamada's formula, and we didn't have to use D4, D5 was nanomaterial, so we didn't use that. So eventually we used 3 different diameters of particle. This is our sand 1, this is our sand 2, cement, silica fume were able to produce the D3, and glass powder, the D3. Now, the green things here, I put them, we didn't use them, but to show that if we needed different diameters, we could have managed that as well. Now, this is visually, some of these, the big sphere here is our 0.5 millimeter sand. The one inside is the 0.11 millimeter. The very, very small one is the 1.1 micron. And then we counted that there might be some non-hydrated cement that can occupy, in the 25 micron range. And this was nanoparticle we didn't use. Okay. But one thing, again, visual, is that, remember, I said, if you add the small spheres to the big spheres in the case of in this case, you add only 1.7%. But if you tried an experiment, like in this case, 95% these beans and 5% whatever lentils, and you put them and shake together, you find that the lentils go down to the bottom. They don't go into the interstitial space. So what you have to do is something more. And one more thing, that something more is that you will pick up 2 sand, for example, sand 1 and sand 2, and you find out that each one may have a bulk density, let's say, they call it small, but when you mix them together, there is a proportion that is going to give you the highest bulk density. And so we needed to pay attention to that in our calculation. The other thing that we did that was, I think, a little bit innovative is that we selected the sand that went in here. We gave it a little bit of a bigger range. We wanted the particle, some particle, to be large or large enough to create an instability in this so that the grain roll more easily. And I think we cannot prove it, but I think it helped. All right, and I'm going to quickly here, because the time is going out, this is the mixture and so on. I just don't want to exceed my time. This gives you an idea of the mixture that we ended up developing. 192 megapascal without fiber, 210 megapascal with fibers, and a spread of the cone test, inverted cone test, which is one of the measure of finding, the flowability of ultra high performance concrete. Our test results were in the range here, in fact, higher, that was published by Professor Failing for a very large number of data. And so we were very confident that we had a good mixture. I know I'm running out of time, but there is a part that I want to cover. Give me some advice, Professor Quirk. I have still some application, and this might take 2-3 minutes more.
Okay, 3 minutes.
3 minutes total? All right. So I'm not going to give you the result. By the way, the results, the detailed result, it doesn't matter. The detailed result exists in the publication and in the book. And I'm going to take slowly the results. One conclusion is that these non-proprietary UHPC mixture developed can be made at a fraction of the cost of the mixture you could buy. And therefore, you should use them. And hopefully, this race of going higher strength, higher performance, etc., will continue, and you will be part of it. Okay? Now, I want to show you some structural application with UHPC. And first one is very, very important, by the way. There is a study that was done by Professor El-Tawi. He took a pre-stressed concrete bridge beam and standard pre-stressed concrete and redesigned it using UHPC. The first observation, the cross section is reduced. So it's just 35% reduction. Because the cross section is reduced, the weight is much less. Then you save on the steel, you save on the cost of transportation, you save on the cost of erection, etc. So now let's look at the calculation he made. He took that beam, he said the cost of the concrete is X, $120. Total other costs, that is transportation, erection, steel, etc., 7X. Total cost of the standard beam, 8X. But when he took the UHPC beam with reduction in weight 35% and the reduction in other costs 30%, he got a total cost of 8.8X. And the issue now, the difference in cost is not so much. If you can get a material that can last for 100 years without maintenance, it's nothing to pay 0.8 more for that case. So that's the first thing that it's very important. So today, if you can develop a non-proprietary UHPC material that costs you essentially 1/3 or 1/4 of the one you buy on the market, you should use it, because at least you could do this kind of comparison to check exactly what you get, and the cost of life, increase in life, service life, should be considered. Okay, so these are I'm going to go through 3-4 of these slides. One is most of the initial application of UHPC were on footbridges. We were still timid. We didn't know what to do. I show you 2 bridges built in Switzerland from Professor Bruweiler. In fact, not far from here in Malaysia, Dr. Bo started with UHPC maybe in the 2005, 6, 7, etc. And so far, I think he has been the one building the most real structure out of UHPC. To his record, he has more like 100 bridges. This is one of them, 100-meter long. Okay, it's UHPC. These are all some of the bridges he's talking about. When you read some of his structures, if you go to the I-beam here, these are typically for less than 32 meters. He can build the whole thing and transport it like this. If it is more than 32 meters, he goes segmental. It's very impressive. When you look at these, how thin they are compared to other structures, it's very good. This is another example of his studies. Okay, and this is the study I mentioned by Professor Tadros, where they developed their own UHPC. I would like you to notice the width here is between 75 and 100 millimeters. These are real size beams. And in fact, he tested beams without stirrups in the middle, and he still got like a factor of safety of 2. So this is the one I want to stop at because it's amazing. This is the roof of the high-speed station in Montpellier in France. It was built using ductile, so white cement. And it's very expensive in a way. However, this is the cross section of each of these beams. Because of the light, you don't see very much, but each you see here and here, this is the beginning and end of a beam. I assume it's like a T-beam. The rib of the beam goes like this. The cross section is here. This cross section contains pre-stressing steel. This here are only 100 millimeter thick UHPC. The lights are integrated glass inside. And the shape of this structure, as you could see, has been designed in such a way, because it's round here and here, that it collects the water. The drainage the water that comes to the roof is automatically drained around. So now by building one roof with light integrated from the outside, no maintenance, hopefully for the next 100 years, and taking care of the drainage, they said it cost them less than if they had built by other methods. This is another example of these very nice facade structure made with UHPC. No continuous reinforcement. It's about 50 millimeters thick. And you see a lot of them now are common in France. Okay, I'm gonna stop almost at this point. Our dream is always to mix fibers into concrete like sand and aggregate to create an isotropic, homogeneous, moldable, strong, ductile, and durable composite for construction applications. Almost similar to reinforced concrete. And I think that dream is getting closer, and you guys are going to be in it in the future. And thank you very much for your attention. And I'm sorry, I've exceeded a little bit my time. But hey, if there is any serious question, I can be reached either by email to Professor Tan or.
Yeah, I think we can have time for a few
Yes, yes, please.
Important one. So,
yeah, I don't have, personally, I don't have any commitment.
Okay.
So I'm
we have a little bit of commitment here in the room. So,
so
maybe Professor Tan will read out some questions he has picked out from the chat.
Okay, actually there are only 3 questions here.
Okay.
And they're quite maybe quite straightforward or maybe not so straightforward, depending on how we see it. Okay, the first question here is to engineers, fibers in concrete is a technological advancement in the built environment, right? So where else do environmentalists fibers, especially synthetic microfibers, are a tragedy? So would you like to comment on your career if you were an environmental conscious engineer or academic, and how sustainable is the use of fibers in the built environment? So to this person is thinking that the use of fiber is not environmentally friendly. So what do you think?
Well, to the same, I guess, to the same extent as regular reinforced or pre-stressed concrete, you could argue that the use of steel can be environmentally friendly unfriendly, because you have the carbon emission and so on. The issue is that if he's thinking about why am I using a small piece of steel versus a large piece of steel, that's an absolutely legitimate question. Effectively, to produce a fiber is less environmentally friendly than to produce a bar. However, one of the main properties that fiber impart to concrete is not strength, is toughness. And to me, there is no other material that I know that would induce in concrete an as large fracture energy or resistance to impact and resistance to. So since we don't have any other option, we have to use some fiber, at least in these options.
Okay. Yeah. So I think that will answer your question. And the next question here is, may I know the performance of UHP-FRC in fire?
Okay, it's a good question, because effectively high performance concrete or high strength concrete tend to let's say crack and explode under fire. And one of the possible remedies is to add a small amount of polypropylene fibers, which when the temperature increases, they basically vanish or disappear, creating tunnels in which the water in the concrete. Now, it turns out that ultra high performance concrete has so little porosity and not much water left anywhere. I haven't run myself a test, but apparently in recent tests, it is behaving very well. So I don't know what it means behaving very well, because I didn't witness the test, but I can tell you the porosity from the packing density, the porosity is less than 2%, and the water binder is so low, there is no water left for something else. In fact, it has some cement particles that are non-hydrated. So if there was any water, it would have been taken by the cement. Okay. I hope it will help. Yes.
Okay, thank you. Next question here is okay, is there is a question here. Is there any I think it's about European specifications, so I mean, never mind. Whether there's any European specification that there are in the market that the industry referring to. He's asking whether there are any European specifications.
Yes.
Yeah.
Actually, the French, the association is like Association Française de Génie Civil, the French Association of Civil Engineers, has already published 2 or 3 guides on ultra high performance concrete. And I looked at some of these guides, and although I don't agree with everything they say, but yes, there are specifications. Now, the ACI Committee 239, which was for only 4 or 5 years ago, is trying to work on a guide for high performance concrete, a guide on the material. Any committee start work, but the French have come up with a specification like an official, it's one like a code.
Yeah.
And in Spain, I know some people are duplicating this, and of course in Germany, yes. But the French have something published.
Yes, I know that also. I think the French standard on high performance.
Yeah.
Yeah,
they had it, and I think it came because, remember, Lafarge is a French company too, and they introduced ductile, and they put the pressure on the on the association to produce something.
Okay, the next question here is what is a reasonable safety factor for the tensile stress at serviceability limit state and ultimate limit state for design purposes? Maybe this one, maybe I'd like to clarify is that in our local standard, which is based on the Euro codes, we use safety factors for material strength.
Yes.
Whereas in America, I think you are using
We have the fee factor for.
So here it is asking what is the reasonable safety factor for the tensile strength
I can try to answer that. If you are using a structure, say according to ACI, you are already designing based on ultimate, okay? But then because it's tension, you are using a fee factor for the material. So you do take the value of the ultimate strength of the material, let's say. You use it in the design according to the factors of the design, which might be 1.7 or 2. And then you reduce the factor on the material itself, the fee factor, because it's tension to 0.65 or something like that. So you in effect reduce the safety on the material, but you are still designing at ultimate with the regular factors, 1.4, 1.7 that are used. So that's the general response, but of course, for every application, you need to look a little bit more closely.
Okay. Right. I just want to substantiate it. Maybe because the way we do it with the Euro code and with the Israel code is a bit different, so we cannot really. In terms of material safety factor, usually we use a factor of 1.5 for concrete.
Yeah.
So in terms of say compressive strength or even tensile strength, this is what we use 1.5.
So if you are using ultimate strength design,
yes.
you use instead of F'(C), you use
Divide by 1.5.
oh.
So,
But then what is the factor of loading? Because I mean, you could use the actual load and reduce the material, or you could use the material and increase the load.
no, we do both.
You do both. Okay, it's fine. I'm just responding according to my experience. But yeah, it could be. I mean, at the end, probably you find out whether you go this way or that way. You end up with the same system.
Probably will be more, in terms of final design will be more.
Yes.
Okay, yes, next question here. For the last one, okay.
Ask the audience here.
Yes, the audience. But anyway, the audience, I might be here in the next few days. Knock at the door.
It's for an engineer name. I say great work, and it's great that we can use FRC, fiber reinforced concrete, to do 3D printing for building without reinforcing bars. As technology advances, the challenge is to allow different or appropriate amount of fibers to be designed and placed at respective locations to meet respective stress requirement under loading for economical design. So it's making a comment that perhaps we can use FRC for 3D printing.
Yes, of course. The 3D printing.
Yes.
As you said, Kiang, we have been using whatever the extruded FRC in the 1960s. Different rheology, but for 3D printing, the same idea. And the other question about is right, that you don't need to put the fiber in all the structure. In fact, when we discuss in class, we say selected zones of structure like beam column connection in seismic zone. You put the fibers there, but you don't need to put it somewhere else. So you save a lot, and you get what you want.
So this can be proven.
Yes.
So it's a good research topic for.
Yes.
Okay, so maybe you want to.
Yes, please. Yes.
I open to the floor. So anybody want to ask any question?
You're all hungry, huh?
I have a lot of questions, but I guess start with this one. The two things you were talking about is UHPC that interests me a lot. Number one is that there's quite a lot of cement that's unhydrated during the life of this material. And secondly, we do need to achieve a very dense packing for the original these globular particles. So this poses a chance for using inert materials. You know, we are dealing with waste materials every day. We're finding a place to use them, but they are always not very reactive. But it's non-reactive cement and this packing density. So to shift them, we can use these not very reactive waste materials. Is that a possibility of developing new?
I think if it's not reactive, you could at least reduce the size so it becomes a particle that increase your packing density. And then maybe if it's a question of if some of it is reactive and you are sure of that, then you proportion it accordingly. I mean, this is what I would do if I understand your question.
Yeah. So
Actually, your waste material, effectively, if you grind it to the level, I mean, I gave some example starting with 0.5 millimeter, but if your grain size is 1 millimeter, then the other particles can be ground to what you think is going to increase the packing density the most.
Okay. Part of the size is the key factor to control here.
I think for the packing density, definitely. And look, we got packing density, what we think, around 80%. Now, a typical concrete is like 67%, and it's very hard to go 1 or 2 or 3% at a time, you know. So, yes, the packing density is very. I thought that when we studied concrete, and I don't know if you and you can they never taught us about packing density, and yet it seemed to be so important. And now I think packing density should be part of the curriculum, should be taught. And why not use sands of different grain to increase your packing density, meaning you increase your durability, your service life. It's amazing system that didn't cost much more, you know, just to think about it.
Yeah, that answers my question well. Thank you.
For the you mentioned about you mentioned about the development of fiber reinforced concrete, about the development in this decade.
Yes.
And you also mentioned the challenges for the next generation.
Yes.
So just wondering what is the main challenges in your opinion?
Okay.
This field?
What I'm talking about, well, I mentioned something. Let me immediately, if you are interested in, are you interested in ultra high performance concrete? Okay. One of the challenge right now, strain capacity. I showed you an example of a curve. And if you remember, if you look at it, one strain was about 2.5%, the other was 4%. Structurally speaking, if you look at the strain diagram recommended in bending by ACI, in order for your fiber to contribute to the ultimate bending resistance of a beam, you need a strain capacity larger than 0.5% or 5/1000. I reviewed in a recent paper that I presented only last October at the ACI convention. I reviewed 97 series of tests of ultra high performance concrete. The total average was 3.4%, 4/1000, which is less than 0.5%. It was 0.34%. And so that in terms of making a difference, trying to find how you could increase the strain capacity with steel fibers. Now, some people have increased the strain capacity with high density polyethylene fiber, HDPE, because the fiber itself has a lower modulus and eventually you get a more fine crack and so it looks like the strain is higher. But with steel fiber, I think it's a challenge, and if I